Okay, the end is in sight, so that's good. We're getting there. So we're going to talk a little bit about graph theory. A graph is a finite, meaning countable, opposite of infinite, finite. You can count it. So finite sets of points, which we call vertices, singular is vertex, and line segments, or curves, and those are called edges. Right? So it's a finite set of points. So normally a line is made up of infinite many points, right? In math, like infinite many points make up a line. In graph theory, that's not the case. So for example, if I give you, this, and maybe it goes there, and goes there, and goes there, and goes there, that literally only has 4 points on it, or 4 vertices, okay? This just means there's a connection. So kind of think of maybe like roads and cities. Like here's a city, there's a road over here, another city, another city, another city. So the cities are kind of like your vertices. There's not infinite many cities. The edge is more like a road or a flight or something like that. Okay, so a little bit different. If they cross like this and there's no dot, there's no city there. So that would kind of be like an overpass. So for example, one road going like this, the other one going, it looks like they cross, but they don't because one's above the other. So if there's no dot there, they do not cross there. One's above the other. If I put a dot there, then it's like there's a city there. And so, yeah, there's a road there, road there, road there, road there. But if there's no vertex there, there isn't one. Okay, just because they cross it does not make a point. Let's see, if I have this, so this is a vertex, singular, if I just have one vertex. So this is kind of like I have a city and then I have this loopy road, right? And that's what we call it. We call it a loop. So an edge that starts and ends at the same vertex, okay, that's called a loop. And it looks like a loop, so that helps, okay? So it starts and ends at the same vertex. That is a loop, okay? Equivalent graphs do not have to look the same. They just have to kind of be the same, okay? So for example, I could have this kind of more pentagon looking graph. So maybe this is A, then B, then C, then D, then E. And you can see like, oh, from city A, I could go to B. From city A, I could go to E. From D, I could go to C. Can't get from D to B directly, things like that. And so then I could draw another one. Maybe it looks like that. Again, that is not a point. That's, again, like an overpass, right? They look like they cross, but one's above the other. And say I put, A, B, C, D, E. Okay, so let's look. If I start here, I go from A to B, and then B to C, B to C, C to D, C to D, D to E, and E back to A. These are the same graph because they have the same number of vertices and they're connected in the same way. So what makes them equivalent is same number of vertices and they're connected in the same way. So there's no extra paths or anything that you could, like there's no way from E to B on either one of these. E can only go to D, E can only go to A, E can only go to D, E can only go to A. So that means the graphs are equivalent. They don't have to look the same, okay? They do not have to look the same at all. All right, degree is super important in this, okay? So degree is how many kind of roads come in and out of the city, or the number of edges at a vertex. And it's coming in and coming out. So for example, these all have 2. There's one coming in, one coming out, right? So those all have degree 2. Same thing over here. A loop has degree 2 as well, because one coming in, one coming out. So that has degree 2. Here I have 1, 2, 3 coming in, so that has degree 3. 1, 2, 3, 1, 2, 3. So we're counting like the roads, 1, 2, 3, or the edges. This one has 4. 1, 2, 3, 4. So that's your degree, okay? If I have something that looks like this, maybe I have a loop. Maybe it comes over here, and then, kind of spokes out a little bit, something like that. Okay. The loop has degree 3 because one coming in, one coming out, and another one. So there's 1, 2, 3 ways in or out. So that's 3. this would be 1, 2, 3, 4, 5 is the degree. These would all have degree 1. Okay, there's only one way. All right, a path. So a path is made up of vertices and edges, and you just kind of travel the path. So if I have, say, this guy, maybe we'll put one in the middle here, so like A, B, C, D, E. A path would just be, say I want to get from A to E or something. So a path might be like, oh, I'm just going to go A and then to C to E, and that's a path. It's not a special path. It's just a path from A to E. Say I want a path from A to E again, I could maybe go up and over and down, okay? Maybe I want a path from A to B, and I go A, C, E, D, and over to B, okay? That's a path from A to B, okay? And the way we usually write that is we'll go like A arrow to C, C arrow to E, E to D, and D to B, okay? Now, there are special paths, which this is one of them, okay? But if it's just between any two vertices, it's just a normal path. We're going to talk about the special paths in a second. Okay, a circuit, again, not a special circuit, just any old circuit, is it kind of goes around, right? Which, like, if you have electrical stuff, sometimes you have circuits in your electrical run through your house, okay? So a path, it starts and ends at the same vertex. So it starts and ends at the same vertex. Okay, so notice a path is just made of connected, vertices, connecting edges, and you don't have to end up anywhere. You just start somewhere and end somewhere else. That's a path. Circuit, you have to come full circle, okay? So if I look at, I'll redraw my example up there. So here's A, here's B, here's C, here's D, here's E. If I start with A, I want to get back to A, okay? So this one, I didn't get back to A, but I could if I wanted to. So if I start at A, and I could do it differently. Say I want to get back to A, I could maybe go A to E, E to D, D to C, C to B, and then I could go back. So I'm kind of traveling that way, okay? And again, there's a special name for that one, but we'll talk about that in a second. A to E, E to D, D to C, C to B, and C to A, okay? And that's a circuit because I got back, okay? That's a special circuit. I could do another circuit that's doesn't get a special name. Okay, so maybe I just want to get back. Maybe I just go from A, right there. Still a circuit. I start at A, then I go to E, then I go to C and back to A. So I start at A and I end at A, but it's not a special circuit, okay? And so what makes these things special is if you kind of, touch certain things, okay? That's what's going to make it special. If you have a bridge, bridges are kind of dangerous, okay? A bridge is like, say I have these over here, and then this, and then I have these over here. Okay, a bridge is something that if you get rid of it, your graph is disconnected. Okay, so right now my graph is all connected. I can get from any city, so to speak, to anywhere else. I might have to drive on a lot of roads, but I can get there. But if I take this out, do you see how the graphs become two and they're separated? They're disconnected. So that is what we call a bridge. Okay, so bridges are kind of maybe like something to keep in mind because sometimes they're a good place to start. Okay, so say I give you something like this. Maybe this is A, B, C, D, and E, okay? So say I want to make a path here, okay? It might be, maybe a good idea to start over here by the bridge because if I take that out, I'm disconnected. So maybe start like D, C, B, A, E, okay? And if I want to get a circuit, that's gonna be a problem if I want D in it, okay? If I don't care about D, I can make a circuit right there, A, B, C, E, and back to A. But if I want to include D, having a bridge is a problem with that, okay? All right, let's see. So we talked about connected, we talked about disconnected, we talked about a bridge. Okay, let's talk about the special ones because those are what we kind of care about. All right, so Euler, it is German. It is not pronounced Euler. It's Euler. And we're going to talk about Euler Path, and then we'll talk about Euler circuit. Okay, Euler starts with E, okay? So he cares about edges, okay? And he's kind of cares a lot about edges because he wants you to touch every single edge exactly once. He doesn't care about vertices, okay? So this is a special path, okay? So we're going to talk about this special path, okay? So you're going to start somewhere. So start at a vertex. So start at a vertex, okay? And then you have to touch every edge exactly once. So you have to touch or go over every edge exactly once, meaning you can't backtrack, okay? So Euler cares about edges. Vertices he could care less about, so vertices don't matter. Meaning if you think of edges as roads, right? You can only go on each road once and you have to go on it. Vertices don't matter, meaning like if you think about those as cities, you know, you could go through the same city multiple times. Nobody cares, okay? All right, so that's an Euler path, and so you can probably guess an Euler circuit, right? Has to touch every edge, but it's a circuit, so you have to start and end at the same vertex, start and end at the same vertex, because that's what a circuit is, right? You go around. But again, you have to touch every edge exactly once. Okay. All right. So, you know, like an Euler path, you know, could be an easy one, right? Like if it just goes like this, right? If I start at A, you know, and I go here, 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 I've touched every edge. That's totally fine. And then an easy circuit down here, you know, like say I just had a rectangle or whatever. If I start at A, I go here, 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 I got back and I touched every single edge, but you cannot backtrack, okay? All right, so, and sometimes they don't exist, all right? So that's the other problem with this. Sometimes you look and you're like, oh my gosh, I can't find it, but there is a theorem to help with that. So say we have this picture. D, and then we'll go down here to F. And again, I think it's easiest to think of the edges as like roads and then the other ones as cities. All right, so let's look at this. An Euler path. Okay, so a path has to touch every edge. Now, again, starting at a bridge is a good idea. Do you see if I get rid of that, then it's not connected, or if I get rid of that one, it's not connected. So maybe if I'm looking for an Euler path, that's probably a good place to start, because do you get if I start in the middle and I kind of go and I get down here, do you see I'm trapped because I can't backtrack? So for an Euler path, probably a good idea, you know, to start maybe here. So let's see if I can get every side. So A, B, C, can I come up here? I think I can get a path. Okay, so let's look at that. If I go A to B, B to C, C to E, E to B, B to D, over to E, down to F, up to D, and down to G. Okay, and again, the way you'd write that, like on my math lab, is A to B, B to C, C to E, E to B, and notice I went back to B. That's okay. You can revisit cities. You just cannot double go on a road. Okay, I think I got it. So A to B, B to C, C to E, E to B, B to D, over to E, down to F, up, yeah. Okay, notice I start at A, ends at G. This is an Euler. I touch every edge exactly once. I don't backtrack. This is an Euler path. It's a path. Trying to get a circuit here starting with a bridge is going to be a problem, because see, if I start at A, like how am I going to get back to A? There's no road. So, you know, sometimes you can't get a circuit, all right? And there is a theorem to help us with that, okay? And so let's see, I'm going to stop this video now. I'll start the next video with the theorem, and that's going to be a huge help to you.